Two small spacecraft left Earth in 1977, aimed toward the giant planets. Not four, not a fleet. Two. And that's the strange part, because the road ahead was not ordinary. Jupiter and Saturn formed the first handoffs. Farther out, Uranus and Neptune sat in the same rare geometry. So why did NASA send only two Voyager probes? The answer is not that approved Voyager 3 and Voyager 4 spacecraft were built and then cancelled. That story is too neat and wrong. What existed first was a bigger grand tour and tops planning lineage. By the end of this video, you will understand why 2 was not a lack of ambition. It was the version of a once-in-generations opportunity that could survive cost, schedule, and spacecraft design. It also had to survive something harder, reaching the road before it changed. And you will understand why Voyager 2's brief ice giant encounters still feel unfinished today. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. The first thing we need to understand is that Voyager was shaped before it ever reached a launch pad. It was shaped by moving planets. Picture the outer solar system not as a set of still targets, but as a slow clock. Jupiter moves, Saturn moves, Uranus moves, Neptune moves. Every one of them is tracing a path around the Sun, and the pattern never freezes for us. A mission planner cannot just point to a planet on a poster and say, "Send the spacecraft there." The planet will not be there when the spacecraft arrives. Now add distance. Jupiter is already far enough that a spacecraft needs years to reach it. Saturn is farther. Uranus and Neptune sit so far out that a direct mission can become a generational project if we ask the launch rocket to do all the work. The problem is not only how far the planets are, the problem is how to arrive with enough speed, in the right direction, at the right time, without building an impossible rocket. That's where gravity assist becomes the key. A gravity assist sounds mysterious until we make it physical. A spacecraft approaches a moving planet. The planet's gravity bends the spacecraft's path. From the spacecraft's point of view, it falls toward the planet and climbs away again. But from the Sun's point of view, the planet is also moving. If the encounter is aimed correctly, the spacecraft leaves with a changed path and a new speed. It has borrowed a tiny amount of the planet's orbital motion. The planet barely notices. The spacecraft notices everything. Now imagine using that trick not once, but again and again. Jupiter can throw a spacecraft towards Saturn. Saturn can bend the path farther outward. Under the right conditions, the chain can continue toward Uranus and Neptune. The planets are not lined up like beads on a string. That image is too neat. The real opportunity is subtler. Their positions create a sequence of handoffs, each one timed so the next planet is where the spacecraft needs it to be, and that sequence was rare. NASA histories often describe the late 1970s outer planet gravity assist geometry as an opportunity that comes roughly once every 175 years. Some public accounts use 176 years. The exact phrasing matters, because it does not mean no mission can ever visit the outer planets outside that span. We have sent spacecraft to Jupiter and Saturn without a full grand tour chain. What it means is that this particular fast sequence, this route through multiple giant planets, was unusual enough that missing it would change the scale of the mission. So the road was temporary. That one idea makes the title question sharper. If NASA had a temporary road through the giant planets, why not fill it with spacecraft? Why not use the opportunity as fully as possible while the clock allowed it? But look at the constraint from the mission designer's side. The road was not a highway already built. It was a set of moving gravitational doors. To use one, the spacecraft had to launch within a window. To use the next, it had to arrive on a narrow path years later. A delay on Earth could become a missed encounter at Jupiter. A slightly different Saturn flyby could erase Uranus and Neptune. A spacecraft failure after launch could end a decade of planning in silence. We often talk about exploration as if the destination is the hard part. In this story, timing is just as hard. The outer planets would still be there in 1985, 1995, and 2005, but the linked route through them would not remain the same. The objects wait, the path does not. Here's the other part. Gravity assist does not make travel free. It makes a certain kind of travel possible. You still need a spacecraft that can live for years. You still need instruments that can work in dim sunlight. You still need radio communication across billions of kilometers. You still need navigation so precise that a flyby can use one planet to aim at another planet years away. And you need money and political support to keep the whole thing alive, long before any photographs can show the public. The temporary road made a wider mission conceivable. It did not make it easy, and that's why Voyager is not just a story about two machines. It becomes a story about a moment when geometry offered more than NASA could safely carry. Before we ask why only two spacecraft flew, we have to see the road that made more spacecraft tempting in the first place. Now we can follow the people who saw that road before most of the world knew it existed. Gary Flandreau is often the name attached to the moment when the Grand Tour became visible. In the mid-1960s, he was a young Caltech graduate student working at the Jet Propulsion Laboratory. His task was not to invent Voyager. It was to examine possible trajectories through the outer solar system. But when he plotted the positions of the giant planets, the pattern became extraordinary. Jupiter could be used as the gateway. Saturn could become the next handoff. With the right launch years, the path could continue outward. Think about what that meant in the 1960s. NASA was still racing toward the moon. Robotic spacecraft had barely begun to turn the planets from lights in the sky into places. Mars had been glimpsed, Venus had been probed. But the outer planets remained almost entirely telescopic worlds. Jupiter and Saturn were familiar names, but not familiar places. Uranus and Neptune were even more distant, cold, small disks in Earth-based instruments, carrying enormous unknowns. A conventional mission to Neptune could take something like 3 decades. A gravity-assist Grand Tour could cut that dramatically, with NASA histories describing possible flight times to the far outer planets in the range of about 8 to 13 years depending on trajectory. Those numbers are not just engineering trivia, they change who gets to see the results. They change whether a mission belongs to one scientific generation or the next. But we should be careful here. Flandreau did not create this world alone. Gravity-assist thinking had roots in earlier celestial mechanics, and in JPL work by people including Michael Minovich. NASA planning groups, university scientists, advisory boards, and spacecraft engineers all mattered. A trajectory paper can reveal a path. It cannot build a spacecraft, defend a budget, reserve a launch vehicle, manage instruments, or keep a mission alive for 12 years. So the more accurate picture is not one lone genius discovering Voyager. It becomes a confluence. Mathematics made the route legible. The post-Apollo moment made ambitious planning urgent. Planetary scientists made the case that the outer solar system mattered. JPL and NASA field centers began turning a geometric opportunity into mission concepts. And once that happened, the dream expanded quickly. Because if you can use Jupiter to reach Saturn and Saturn to aim beyond, it becomes very hard not to ask the obvious question, why stop there? If the road reaches Uranus and Neptune, why not keep going? If Pluto can be reached on another branch, why not include it too? If the alignment is rare, why not treat it as a once-in-generations survey of the outer solar system? That's the emotional pull behind the Grand Tour. It was not only a mission plan, it was the feeling that the solar system had briefly opened a door. But a door in the sky is not the same as an approved program on Earth. The path from calculation to mission had to pass through the realities of NASA in the late 1960s and early 1970s. That means budgets. it means advisory committees. It means arguments inside the scientific community about whether one enormous mission should dominate planetary exploration. It means spacecraft technology that had to survive far beyond the inner planets. It means the simple problem of committing to operations years before the most distant payoff. Now the title question begins to split into two questions. The first is easy to feel: why not send more? The second is harder and more important. What kind of mission could survive long enough to leave Earth before the road changed? The Grand Tour would be the first serious attempt to answer that. Each constraint changes the answer in a different way, not as a list of excuses, as the evidence for why this mission became the shape it did. The geometry constraint came first because it was the only reason the Grand Tour question existed. If Jupiter, Saturn, Uranus, and Neptune had not created a usable sequence of gravity assists, there would be no serious mystery about why NASA did not send a wider multi-planet fleet in 1977. A mission can always dream of visiting many worlds. The rare part was that the planets briefly made that dream efficient enough to study seriously. But geometry is not a permission slip. It becomes an opening. It says the route can work if everything else happens in time. It does not build the spacecraft. It does not guarantee the budget. It does not extend the launch window because a committee needs another year. It does not care whether a new spacecraft design is late, so the first constraint has two faces. It creates the opportunity and it punishes delay. So that's why this story is not like deciding how many copies of a satellite to place in Earth orbit. The outer planets move on humanly inconvenient schedules. If the mission missed the late 1970s sequence, NASA could not run the same Grand Tour a few years later with the same flight times and the same chain of encounters. The road would be different, the handoffs would be different, the mission would be different. Now we can hear the word temporary with more force. A temporary road increases the value of ambition, but it also lowers the tolerance for development risk. A bigger mission that arrives late can lose to a smaller mission that arrives on time. Here's why Mariner heritage mattered. It was not glamorous to use a more conservative spacecraft lineage. It did not satisfy the full TOPS dream. But heritage made schedule more believable. In a mission ruled by moving planets, believable schedule is not bureaucracy. It's physics translated into project management. The pieces of the story belong here, inside the mission itself. The route was rare, the larger concept was real. The approved mission was smaller. The two spacecraft were not an accident. Voyager 1 and Voyager 2 became different answers to the same temporary road. And the ice giants still carry the consequence. But before we close, it's worth holding those pieces together, because this becomes where the familiar Voyager story usually becomes too simple. The Grand Tour begins with a strange kind of discovery. No telescope image changed overnight. No spacecraft sent back a signal. Nothing exploded, vanished, or appeared in the sky. The discovery was a pattern in motion. It was the realization that the giant planets, moving slowly around the Sun, would briefly permit a route no single rocket could easily create by brute force. Now picture that in the world of 1965. NASA was huge, but not infinite. Apollo was taking most of the oxygen. The United States was preparing to land humans on the moon, and planetary science was still learning how to speak with confidence about worlds beyond Mars. A spacecraft going to Jupiter was already ambitious. A spacecraft reaching Neptune by using a chain of planetary handoffs sounded almost unreal, but not impossible. That was the important word. Gary Flandreau's 1965 work helped show that a fast reconnaissance of the outer solar system could be designed around Jupiter's gravity. Public histories often describe him plotting the positions of Jupiter, Saturn, Uranus, and Neptune and realizing that the late 1970s configuration would not repeat for roughly 176 years. The number is memorable, but the deeper point is not the number. The deeper point is that a human schedule had collided with a planetary schedule. We can miss a launch window the way we miss a train, but this train was made of planets. Now, if we tell the story only through Flandreau, we make it too small. The paper and the calculation mattered, but Voyager was not a magic trick pulled from one desk. Earlier JPL trajectory work had explored how planetary gravity could reshape interplanetary paths. Michael Minovich's technical work is part of that background. NASA's Space Science Board studies and planetary advisory processes were asking what outer planet exploration should look like after the inner planets. Engineers were thinking about power, communication, and spacecraft longevity. Scientists were thinking about atmospheres, rings, moons, magnetospheres, and the basic reconnaissance of worlds no machine had visited. So let's widen the image. A young trajectory analyst sees a road. A laboratory has the mathematical culture to understand it. A space agency has the ambition to take it seriously. A scientific community has questions waiting at the end of it. And the planets, indifferent to all of this, keep moving. That's how a calculation becomes pressure, because once the route is recognized, delay becomes costly. If NASA waits for a perfect spacecraft, the geometry can slip. If it builds too small a mission, it may waste a rare chance. If it builds too large a mission, it may collapse under cost before it ever launches. Every option carries a risk. Here's where Voyager becomes more interesting than nostalgia. The familiar story says 2 heroic spacecraft survived for decades. True. But before they survived space, the mission idea had to survive Earth. It had to survive human institutions, annual budgets, engineering reviews, scientific disagreements, and political priorities. And the timing was awkward. Apollo made enormous things feel possible. It also made them expensive. By the time the outer planet opportunity was becoming serious, NASA was already facing a different future. The agency that had been built for the moon could not assume Apollo-level growth forever. Federal priorities were shifting. The public mood was changing. The question after the moon was not only what can we do, it was what can we still afford to do, and what can we keep doing long enough to matter. Planetary scientists were not all saying the same thing either. Some wanted broad reconnaissance. Some wanted focused missions. Some worried that a massive outer planet program would consume money that could support other investigations. That does not make them villains. It makes them scientists and institutions working inside scarcity. Here's a useful way to think about it. The Grand Tour was not competing only against indifference. It was competing against every other good idea NASA might fund. Mars, Venus, Earth science, astronomy, human spaceflight, the shuttle, technology development, launch vehicles, ground networks. Every ambitious mission claims that its moment is unique. In the Grand Tour's case, that claim was physically true. But physical truth does not automatically win a budget. Now imagine being a planner at JPL or NASA headquarters. You can see the route, you know the clock is moving, you know the science is enormous. You also know that the farther the mission goes, the longer the commitment becomes. You are not asking for a spacecraft that works for 6 months, you are asking for a system that can function for years, maybe beyond a decade, in cold, dim, distant space. Power becomes a central issue. Solar panels are not practical for the far outer planets in that era because sunlight fades with distance. The spacecraft need radioisotope thermoelectric generators, devices that turn heat from radioactive decay into electricity. The phrase sounds technical, but the image is simple. A deep space spacecraft carries its own slow, fireless heat source because the sun becomes too weak. Communication becomes another issue. A spacecraft near Neptune is not shouting into a nearby receiver. Its signal spreads across billions of kilometers before Earth tries to hear it. Commands take hours to arrive. Data returns slowly. Navigation errors have years to grow. And if the mission includes more spacecraft, more encounters, and more instruments, Earth itself needs enough antennas. operators, and attention to listen. So the people who saw the road also saw the trap. A rare opportunity invites ambition, but the very rarity of the window punishes delay, and the very distance of the destinations punishes complexity. That's the central tension of this entire story. A bigger mission could use more of the road. A smaller mission had a better chance of reaching the road at all. The Grand Tour concept would live inside that tension. It would become the dream people remember when they ask why only 2 Voyagers flew. But before we answer that question, we need to understand what the bigger mission was, because it was not Voyager 3 and Voyager 4 waiting in the wings. It was something larger, earlier, and more fragile. There's one last constraint, quieter than the others. Human attention has a scale. We can imagine a mission across 12 years in one sentence. But living through 12 years is different. People change jobs, budgets change, administrations change, technologies change. Public interest rises and falls. A spacecraft that leaves Earth in one political era can reach its final planet in another. The mission has to be designed not only for space, but for the human time it must cross. Voyager crossed that time. The team that saw the route in the 1960s, the managers who saved the smaller mission in the 1970s, the operators who guided encounters in the 1980s, and the scientists who still use the data today are connected by a chain almost as delicate as the gravity assists themselves. Here's why the story feels so moving when told accurately. It's not only that 2 small machines traveled far, it's that a human institution managed to hold a fragile opportunity long enough for those machines to make it real. Now the answer is ready to be spoken in full. NASA sent 2 Voyager probes because 2 was the mission that fit through every constraint at once. Geometry created the opening. TOPS and Grand Tour planning showed the larger ambition. Budget and schedule narrowed it. Mariner heritage made it buildable. 2 spacecraft made it redundant and strategically flexible. Saturn split the paths. Voyager 2 carried the farther road. Uranus, Neptune, and Triton revealed both the glory and the limit of that decision. That's not a small answer. It becomes the reason the 2 Voyagers still matter. There's a quiet human point inside this history. The people who planned Voyager had to make decisions without the comfort of Voyager's later legend. They did not know the spacecraft would become cultural icons. They did not know Voyager 2 would still be healthy at Neptune. They did not know that images from Uranus, Neptune, and Triton would define those worlds for decades. They were choosing among uncertain futures, each one expensive, fragile, and incomplete. That makes the restraint in the final mission more understandable. It also makes the success more moving. The 2 spacecraft were not chosen because the outer solar system was small. They were chosen because the route was large. The risk was real, and the mission had to survive long enough to use even part of it. So the fairest reading is not that NASA settled for too little, or that NASA achieved everything. The fairest reading is that NASA preserved a launchable path through a rare opening, and the 2 Voyagers stretched that path to its limit. The phrase Grand Tour sounds almost romantic. It suggests a sweeping journey, a deliberate crossing of the outer solar system, one world after another. Jupiter, Saturn, Uranus, Neptune, maybe Pluto on a separate branch. A once-in-generations outward passage before the planets moved on. But the Grand Tour was not one simple mission drawing. It was a planning lineage. It changed as engineers, scientists, NASA managers, and budget officers tried to turn the rare geometry into something real. And this becomes where the biggest misunderstanding begins. When people ask why NASA only sent 2 Voyager probes, they sometimes imagine a 4-probe Voyager program. Voyager 1 and 2 flew. Voyager 3 and 4 did not. So the story must be that 2 were cancelled. That's not the right frame. The larger Grand Tour and TOPS concepts came before the approved Voyager mission has flown. They were studied architectures, not an approved hidden fleet of finished Voyager spacecraft. The mission that eventually launched was the two-spacecraft Mariner Jupiter-Saturn mission, renamed Voyager in 1977. If we blur those stages, we get a more dramatic story, but a less truthful one. So let's define the bigger idea carefully. One version of the Grand Tour contemplated 4 launches, often described as 2 pairs. One pair could use Jupiter and Saturn to reach Pluto opportunities. Another pair could use Jupiter, Uranus, and Neptune. The exact studies evolved, but the principle was clear. More launches and more capable spacecraft would use more of the rare gravity assist geometry. Now add TOPS. TOPS stood for Thermoelectric Outer Planet Spacecraft. It was an ambitious, long-lived spacecraft concept associated with the larger Grand Tour vision. The name sounds dry, but the ambition was not dry at all. A TOPS-style spacecraft would need to survive for years in deep space, operate far from the sun, carry scientific instruments, communicate over enormous distances, and remain reliable through multiple planetary encounters. In other words, it was not just build 2 more Voyagers. More spacecraft meant more launches, more launch vehicles, more instrument sets, more testing, more operations teams, more deep space network time, more science planning, more navigation, more money spread across more years, and more ways for the whole program to be questioned before the most distant results arrived. Look at it from the outside, and the Grand Tour feels obvious. A rare road opens. Use it. Send everything you can. Look at it from the inside, and the problem changes. Every additional spacecraft is not just another copy. It becomes another long-term promise. It must be built, launched, tracked, commanded, protected, and explained to budget officials for years. If the spacecraft is more capable and less proven, the risk rises. If the program is larger, the political target grows. If the launch window is finite, every design delay becomes dangerous. So that's why the bigger plan was both beautiful and vulnerable. It was beautiful because the science was enormous. The outer planets were not just larger versions of Earth. Jupiter was a system of storms, magnetism, radiation, and moons. Saturn carried rings, and Triton, a moon with an atmosphere thick enough to demand close attention. Uranus and Neptune were ice giants, a different class of world, with unknown interiors and distant moons. Pluto, still considered a planet at the time, represented the far frontier of planetary reconnaissance. A full Grand Tour promised a first survey of almost everything beyond Mars that had not yet become a place, but it was vulnerable because it concentrated too much hope in one enormous package. Big science has power. It also has gravity. It can pull funding away from smaller missions. It can invite scrutiny. It can become hard to change once it starts. And if a large mission slips past a rare launch opportunity, the whole architecture can lose the route it was designed to exploit. Now we should pause on the word cancelled, because it can mislead us. NASA sources do describe the original larger Grand Tour plan as being cancelled or replaced in the early 1970s because of anticipated costs. That language is real when it refers to the Grand Tour/TOPS architecture. But it's not the same as saying NASA cancelled approved Voyager 3 and Voyager 4 spacecraft. The distinction matters because the viewer came here for a real answer, not a myth with better lighting. What disappeared was the larger architecture. What survived was a smaller mission that could still catch part of the route. The approved mission would focus on Jupiter and Saturn. It would use 2 spacecraft based on Mariner heritage to reduce risk and cost. It would not formally promise the entire outer solar system. Yet within that smaller mission, planners preserved something crucial. If the first spacecraft succeeded and the second survived, The second might continue toward Uranus and Neptune. That small, preserved possibility is the hinge of Voyager. Because the Grand Tour did not vanish completely, it became embedded as an option inside a mission that officially looked narrower. The dream was reduced but not erased. It became conditional. If the spacecraft survived, if the encounters worked, if the budget continued, if the navigation stayed precise, if the power lasted, if the second trajectory could be kept alive. So the bigger mission people remember was real as planning. The rare route was real as geometry. The scientific hunger was real. But the approved Voyager mission was not the full Grand Tour under another name. It was the version that survived the next filter. And the next filter was brutal. The Grand Tour had to pass through early 1970s NASA, where the agency's Apollo-era momentum was fading and every large new commitment had to justify itself in a colder budget climate. The first simple story says NASA had 4 Voyagers and cancelled 2. That story is attractive because it gives the viewer a clean grievance. It also gives the title question a dramatic villain. 4 should have flown. 2 were taken away. Someone made a bad choice, and history has been paying for it ever since. But that story does not match the careful history. The larger Grand Tour and TOPS concepts were studied, debated, costed, reshaped, and ultimately not flown in their fuller form. The approved mission that became Voyager was the 2 spacecraft Mariner Jupiter-Saturn mission. The name Voyager came late. The famous spacecraft did not begin as the first 2 members of an approved 4 spacecraft Voyager fleet, so we should let that false story go. The second simple story says there was never a bigger opportunity, and Voyager was always exactly what it needed to be. That story is also too neat. It protects Voyager's triumph by erasing the reduction. But the reduction was real. The Grand Tour geometry did invite a broader campaign. NASA and JPL did study more ambitious architectures. The scientific case for wider reconnaissance was not imaginary. Uranus, Neptune, Triton, and Pluto were not decorative add-ons. They were worlds sitting behind a rare gravity-assist door, so we should let that comforting story go too. The truthful story sits between them. A bigger opportunity existed. A bigger architecture was studied. That architecture did not survive. A smaller mission did survive, and then the smaller mission did something so extraordinary that it became hard to remember how narrow the thread had been. Voyager 2 is the reason that narrow thread feels almost mythical. It flew past Jupiter, it flew past Saturn, it reached Uranus, it reached Neptune. It became the only spacecraft to study all 4 giant planets at close range. It carried the spirit of the Grand Tour, even though the full Grand Tour architecture had not flown. Now go the other direction. Suppose NASA had insisted on the fuller Grand Tour/TOPS architecture and refused to accept the smaller Mariner Jupiter-Saturn compromise. In the ideal version, the program survives. 4 launches fly. Multiple spacecraft use the rare route. The outer planets receive broader reconnaissance. Uranus and Neptune are not left to 1 spacecraft. Pluto may have become part of the early reconnaissance era. That's the dream version. But missions do not live in ideal versions. In the risk version, the larger program takes longer. The design grows, the cost rises. A budget office pushes back, a launch window approaches. The agency is asked to choose between a huge mission that may not be ready and a smaller mission that can be ready. If the larger architecture fails too late, there may be no replacement. The rare geometry passes, and the solar system receives neither the full Grand Tour nor Voyager as we know it. That's not a claim that failure was certain. It becomes the reason managers feared the larger architecture. A big mission can be more scientifically rewarding and less institutionally survivable at the same time. Here's one of the hardest truths in exploration. Sometimes the maximal mission is not the mission most likely to produce the most science, because the maximal mission may not launch. A smaller mission that launches can return more data than a perfect mission that dies in review. Voyager is the strongest possible example because the smaller mission did launch, and then exceeded its official center of gravity. It did not make the lost possibilities meaningless. It made the surviving possibility enormous. The easiest version of this story has a villain. NASA had a dream. Someone killed it. 2 spacecraft flew instead of 4. The end. But the real story is more useful and more serious, because the villain is not a person. It's constraint. By the early 1970s, NASA was no longer the agency of endlessly rising Apollo budgets. NASA history records a steep decline from the mid-1960s peak into the early 1970s, from about $5.2 billion in 1965 to a little over $3 billion in 1972. Those are historical dollars, not modern converted dollars, and the exact comparison should not be stretched beyond its source. But the direction is enough. The agency was shrinking while the outer planet opportunity was asking for a larger commitment. Now put that decline in context. The United States was paying for the Vietnam War. Great Society programs had reshaped domestic spending. The Nixon administration brought a more conservative fiscal environment. NASA was trying to define itself after Apollo. Human spaceflight priorities were moving toward the shuttle. Planetary science had to fight for attention inside a system where every major program could claim national importance. This does not mean the shuttle alone killed the Grand Tour. That would be too simple. It means the Grand Tour entered an agency full of competing futures, and the Grand Tour was expensive. NASA histories give projected costs for the larger 4-mission Grand Tour in the range of roughly $750 to $900 million. Plus launch vehicle costs, while some NASA summaries describe the larger plan as approaching about $1 billion. The lower-cost Mariner Jupiter-Saturn alternative was far cheaper, around $360 million in the historical NASA history comparison. These numbers should be heard as approximate historical program figures, not as a neat modern price tag. Still, the scale difference mattered, but cost was not just price. Cost meant years of vulnerability. A mission that needs money over a long time must be defended over and over. Each budget year is another chance for delay, reduction, or cancellation. A large spacecraft program can survive one review and still die in the next. A mission aimed at Neptune may not produce its most dramatic scientific payoff until more than a decade after the first money is spent. That's hard for any institution. It's even harder when the launch window will not wait. Here is the trap. If NASA chose the more ambitious spacecraft architecture, it might use more of the Grand Tour. But designing something more ambitious could take longer. Longer development increases the risk of missing the very geometry the mission was built around. If NASA chose a simpler, heritage-based spacecraft, it might lose some ambition, but it had a better chance of launching before the sky changed. So the trade-off was not ambition versus laziness, it was ambition versus survivability. Now add technical risk. A spacecraft for the full outer planet Grand Tour had to work far from the Sun, survive intense radiation near Jupiter, remain healthy over years, and keep sending data through a radio link that became weaker with distance. It had to carry instruments capable of returning meaningful science at worlds no spacecraft had visited. It had to navigate past one planet in a way that set up the next encounter. It had to do this while the ground system kept listening and commanding through long delays. And if the program involved 4 launches, the complexity multiplied. More launches can mean more science. They also mean more opportunities for failure. A launch vehicle can fail. A spacecraft can fail, an instrument can fail, a trajectory can become unusable, a ground network can be overloaded, a budget can be cut, A decision made in Washington can erase an option years before the spacecraft reaches the planet that option was meant to serve. Planetary scientists themselves had mixed incentives. A single giant outer planet program could produce extraordinary data, but it could also dominate the field. If one enormous mission consumes the available money, other missions wait, other planets wait, other research communities wait. The debate was not science versus anti-science. It was different visions of how a limited planetary program should be balanced. We should let that complexity remain in the story, because if we flatten it into NASA not caring, we miss the actual lesson. The Grand Tour failed to survive not because the route was unimportant, but because importance is not enough. A mission also needs a spacecraft architecture that can be built, a budget that can be defended, a schedule that can meet the window, and a risk profile that managers can accept. Now think about the phrase "only two" again. From the Grand Tour perspective, 2 was a reduction. From the budget and schedule perspective, 2 may have been the difference between flying something and flying nothing. If the full architecture collapsed and no smaller mission replaced it, the rare road might have passed with no Voyager at all. That possibility should change how we hear the story. The question is not why NASA took a perfect plan and made it worse. The question is how much of an almost too large opportunity could be saved inside a mission that had a chance to launch. That answer became Mariner Jupiter-Saturn, a smaller name, a narrower official target, 2 spacecraft, Jupiter and Saturn first. And hidden inside the mission design, one remaining thread of the old Grand Tour road. Budget is the easiest constraint to misunderstand, because money can sound less noble than science. But in space exploration, money is time, labor, testing, launch vehicles, instruments, operations, ground systems, and continuity. A budget cut is not an abstract subtraction. It can remove a spacecraft. It can delay a test, it can shrink a team, it can force a simpler design, it can end a mission extension before the most distant science arrives. NASA history's cost comparisons are stark enough without dramatizing them. The larger Grand Tour/TOPS architecture sat in the high hundreds of millions of historical dollars and was described in some NASA summaries around the billion-dollar scale. The Mariner Jupiter-Saturn alternative was substantially less expensive. In a shrinking post-Apollo NASA, that difference mattered. Now, if the only question was scientific value, the larger mission might look obvious. But NASA did not spend scientific value. It spent appropriated dollars across fiscal years. The mission had to survive the Office of Management and Budget, NASA headquarters, Congress, internal priorities, and public justification. It had to compete with other missions that also had strong scientific claims. So budget pressure did not just reduce ambition, it selected for missions that could be defended repeatedly. A smaller mission is not automatically better, but a smaller mission can be easier to protect long enough to launch. In the Grand Tour case, that distinction may have made all the difference. The 2 spacecraft Voyager mission was not the biggest scientifically imaginable use of the route. It was the version that could keep enough support to become hardware. Institutions are made of people, but they are also made of procedures, priorities, rivalries, and memory. NASA in the early 1970s was not a single mind choosing between exploration and non-exploration. It was a large agency moving from Apollo into an uncertain future. Human spaceflight had its own momentum. Planetary science had its own ambitions. Field centers had interests. Advisory groups had disagreements. Budget officials had limits. Scientists had different ideas about whether one large outer planet program should dominate the field. That institutional texture matters because it prevents a cartoon version of the story. No serious account needs a villain twirling a mustache over Uranus and Neptune. The larger Grand Tour was vulnerable because it was big, expensive, technically ambitious, and concentrated. Those qualities can make a mission inspiring. They can also make it harder for an institution to carry. Now look at the Mariner Jupiter-Saturn compromise. It gave different parts of the institution something they could accept. It preserved high-value Jupiter and Saturn science. It used a more credible spacecraft heritage. It reduced the visible cost and risk. It left a possible extension to Uranus and Neptune, without making the entire mission depend on that promise from the start. That kind of compromise is not as emotionally satisfying as the full dream. But institutions often move by survivable compromise. Voyager became historic because the compromise did not erase the road completely. One clarification protects this answer from drifting back into myth. This was not a story about NASA lacking imagination. The imagination was there. The Grand Tour itself proves it. The trajectory work, the TOPS studies, the 4 launch concepts, the ambition to reach worlds no spacecraft had ever seen. All of that came from people thinking far beyond the immediate and the safe. This was also not a story about NASA having unlimited ability and choosing not to use it. The ability was partial. The agency could imagine more than it could carry. That gap between imagination and carrying capacity is where the mission narrowed. It's easy to mock that gap from the future after Voyager's success makes the technology feel inevitable. But in the early 1970s, the future was not guaranteed. A spacecraft aimed at Neptune was a promise to a world 12 years away. A 4-spacecraft architecture was 4 promises, each with its own long shadow, and this was not a story about Voyager being small. 2 spacecraft across the giant planets is not small. 2 spacecraft surviving Jupiter and Saturn is not small. One of them continuing to Uranus and Neptune is not small. The word only belongs to the comparison with the larger Grand Tour opportunity, not to the achievement itself. That distinction is the whole emotional balance. Only 2, compared with what the rare route invited. 2 compared with the risk of none. Only 1 when Voyager 2 reached Uranus and Neptune. 1, but enough to change everything we knew. Now the answer can stay precise. NASA did not cancel approved Voyager 3 and Voyager 4 probes. NASA did not fly the fuller Grand Tour/TOPS architecture. Instead, it approved and launched a 2-spacecraft Mariner Jupiter-Saturn mission, renamed Voyager. That preserved an option for the farther planets. The option survived. Voyager 2 used it. The result was both one of the greatest successes in space history and a reminder that first reconnaissance is not the same as completion. So that's why the story still holds attention after all these years. It isn't just about machines that traveled far. It becomes about how much of a rare opportunity can fit through the narrow opening between physics and human limits. Mariner Jupiter-Saturn does not sound as mythic as Voyager. It sounds practical, almost plain, and that plainness is the point. The mission that survived the collapse of the larger Grand Tour/TOPS architecture was not originally presented as a grand 4-planet fleet. It was a 2-spacecraft mission focused on Jupiter and Saturn, built from Mariner heritage rather than from the full new TOPS vision. The spacecraft were known as Mariner 11 and Mariner 12 until March 7, 1977, when NASA Administrator James Fletcher announced the new name Voyager. That timing matters. Voyager as a name arrived late. The famous brand did not begin as an approved 4-probe program. The approved mission that launched was the 2-spacecraft Survivor of a larger planning history. Now, Survivor can sound like a lesser thing, but in mission design, survival is not a small achievement. A spacecraft cannot change science if it never leaves Earth. A mission that misses its launch window because it was too ambitious may preserve its purity on paper and lose the planets in reality. So Mariner Jupiter-Saturn did something crucial. It kept the mission executable. Using Mariner heritage reduced some development risk. The basic idea was not to create the most capable imaginable outer planet spacecraft from scratch. It was to build something capable enough, reliable enough, and ready soon enough to catch the late 1970s window. 2 spacecraft would be launched in 1977. Both would visit Jupiter and Saturn. That alone was enormous. No spacecraft had yet flown through those systems at close range. But the old Grand Tour did not completely disappear. In 1974, mission planning preserved a conditional path. If the first spacecraft succeeded at Jupiter and Saturn, and if the second spacecraft remained healthy, the second could be redirected onward to Uranus and Neptune. The approved mission did not promise the entire Grand Tour as its baseline, but it kept a door open. That door is one of the most important details in the whole story, because it shows that NASA did not forget the rare geometry. The agency narrowed the mission, but the mission design still carried a memory of the larger opportunity. It was a compromise with a hidden extension. Jupiter and Saturn were the official center of gravity. Uranus and Neptune remained possible, if everything went well enough. But that conditional language mattered. A mission promise is not the same as a mission option. A promise has to be defended as part of the baseline. It shapes budgets, schedules, instruments, operations, public expectations, and failure criteria from the beginning. If the mission promises Neptune, then a failure to reach Neptune looks like a broken mission. If the mission promises Jupiter and Saturn and preserves Neptune as an option, then the same outer road can survive inside a smaller political and engineering container. That may sound like paperwork. It was not paperwork. It was how the old Grand Tour threads stayed alive. Think about what the managers were doing. They were trying to protect a fragile possibility without making the whole project collapse under the weight of that possibility. They could not sell the full dream in its most ambitious form. They could not pretend the dream had never existed. So they built a mission whose official burden was narrower, while making sure the trajectory design did not burn the bridge to the farther planets too early. Here's a subtle kind of ambition. Not the ambition of announcing the largest possible mission, the ambition of designing a smaller mission so carefully that it might grow if reality allowed it. And that's why the wording around Voyager matters so much. If we call the Uranus and Neptune extension the original guaranteed mission, we erase the risk. If we call it an accidental bonus, we erase the planning. The truth is, between those two eras, the farther road was deliberately preserved, but conditionally preserved. It depended on spacecraft health, navigation success, mission extensions, ground support, and the decision to keep going after the original center of gravity had been satisfied. Now picture the planning room with that distinction in mind. Jupiter and Saturn are the defended mission. Triton is a major prize. The spacecraft design has to be ready for 1977. The cost has to stay inside a shape NASA can carry, and yet, in the trajectory mathematics, a quieter question remains. Can we aim one spacecraft so that Saturn does not become the end? That question changed everything. Because once one spacecraft kept the outward geometry, the mission held 2 layers at once. On the surface, it was Mariner Jupiter-Saturn. Underneath, it still contained a narrow passage from the older Grand Tour imagination, not the full architecture, not the 4-launch dream, a passage. That passage was fragile. A failed instrument could reduce its value. A malfunctioning scan platform could cripple the science. A power problem could shorten the future. A budget decision could stop the extended mission before the ice giants. A navigation error at Saturn could close the downstream route. The fact that the passage existed did not mean it would be used, but without that passage, Voyager 2 could not have become the spacecraft we remember. So the compromise did more than cut the mission down. It rearranged ambition into layers. The first layer was what NASA could approve. The second layer was what the spacecraft might still do if the first layer worked. That layered design is one reason the Voyager story feels almost impossible in hindsight. The mission did more than meet its baseline. It unfolded into the option hidden inside it. Now look at the 2 spacecraft as a strategy. One spacecraft could secure the highest priority Saturn science, especially Titan. The other could preserve the outward path. One could take the certain prize. The other could carry the long gamble. That split only works if the mission has at least two spacecraft. A single probe would force all choices into one trajectory. Two probes gave the mission room to breathe, but two also kept the program within a smaller footprint than the full Grand Tour. Two launch vehicles instead of four. Two spacecraft instead of a larger fleet. Fewer instrument sets. Less long-term operational complexity. Less budget exposure. Less hardware development risk. Still difficult. Still expensive. Still audacious. But more defensible. Here's why only two is such a deceptive phrase. To us, with decades of hindsight, two Voyagers can feel inevitable. They launched, they worked, they transformed planetary science. Voyager 2 reached all four giant planets. Voyager 1 crossed into interstellar space. The mission became larger in history than it looked on paper. But before launch, 2 was not inevitable. 2 was a gamble inside a narrowed budget. 2 spacecraft had to survive launch. They had to survive Jupiter's radiation environment. They had to remain controllable across huge distances. They had to return science from worlds never visited before. And for Voyager 2 to become the outer planet legend we remember, the spacecraft had to keep working long after the approved mission's original center of gravity. Here's the phrase that should stay with us. The smaller mission was the mission that could leave Earth. That does not erase the opportunity cost. It does not mean the larger Grand Tour was silly. It does not mean 2 spacecraft were enough to know the outer solar system. But it does mean the reduction preserved something real. Without the compromise, the rare road might have been more fully imagined and less fully used. Now, by the time the spacecraft were renamed Voyager and prepared for launch, the public story had become cleaner. Voyager 2 launched first, on August 20, 1977. Voyager 1 launched second on September 5, 1977, but followed a faster path and would reach Jupiter and Saturn first. Already the mission had a slight strangeness in it. Number 2 left before Number 1, and Number 1 arrived first. That's not a trivial detail. It reminds us that mission names are human labels placed over celestial mechanics. The planets do not care what order we number the spacecraft. They care about paths, speeds, and arrival times. The 2 Voyagers were not just 2 copies thrown into the dark. They were 2 carefully timed attempts to use a temporary planetary road while staying inside the mission NASA could approve. That made the architecture narrower than Grand Tour, but also more resilient. Now the next question becomes obvious. If 2 was the version that survived, why did 2 make engineering sense at all? Why not 1? Why not still push for more? What did the pair allow that a single spacecraft could not? To answer that, we have to stop thinking of 2 as a count and start thinking of it as a risk management system. The spacecraft constraint was just as real. A full Grand Tour spacecraft had to be more than a camera with a radio. It needed power far from the sun. It needed instruments for multiple kinds of worlds. It needed thermal control, attitude control, navigation capability, onboard fault protection, and enough reliability to survive years of cruise between planetary encounters. It had to pass near Jupiter, where radiation can damage electronics, and then remain healthy far beyond Saturn. Now imagine adding more spacecraft to that architecture. If the spacecraft are simple copies, they may not do all the science the Grand Tour asks. If they are more capable, they become more expensive and harder to finish on time. If they carry too many instruments, they become heavier and more complex. If they are stripped down too far, they may reach the planets but miss the measurements that justified the mission. Every spacecraft is a compromise between what science wants and what engineering can trust. Voyager's flown design was extremely capable, but it was still a design built under constraint. The mission could not be endlessly redesigned to satisfy every possible outer planet question. The more the project grew, the more it risked missing the window. The more it simplified, the more science it risked leaving behind. That's the kind of trade-off that does not produce a clean emotional answer. It produces a mission, and it helps explain why not just send more is not enough. More of what? More copies of a narrower spacecraft? More new TOPS spacecraft with greater capability and greater risk? More launches with more operations and more years of budget exposure? Each answer changes the mission's chance of flying. Launch is often treated as the beginning of a space mission. For Voyager, launch was also a deadline imposed by the planets. The two spacecraft launched in 1977, Voyager 2 on August 20, and Voyager 1 on September 5. The numbering feels backward because the trajectories mattered more than the names. Voyager 2 left first but took a slower path. Voyager 1 left later and reached Jupiter and Saturn first. That odd ordering is a reminder that mission design follows celestial mechanics, not human tidiness. A larger grand tour architecture would have needed more launch opportunities, more launch vehicles, and more schedule confidence. 4 launches do not just double the ambition of 2, they multiply the number of ways schedule can go wrong. One delay can ripple. One launch failure can change the scientific value of the whole sequence. One spacecraft arriving at the wrong time can lose a downstream handoff. Now picture the pressure on managers. They could try to preserve more of the grand tour by building a bigger launch set. Or they could preserve the chance of a successful Jupiter-Saturn mission with 2 launches in the window while keeping one path outward if conditions allowed. The second choice is narrower, also more robust. Here's not an argument that 2 was ideal, it becomes an argument that 2 was coherent. The 2-launch plan fit the surviving mission architecture. It gave redundancy without turning the program back into the huge vulnerable structure that had just failed to survive. At this point, the title question can be answered plainly. NASA sent 2 Voyager probes because the full Grand Tour/TOPS architecture was too large and vulnerable for the early 1970s budget, schedule, and technical environment. While the 2 spacecraft Mariner Jupiter-Saturn mission was the version that could launch in time and still preserve one path toward Uranus and Neptune. That's the compact answer. But the compact answer only works after we have earned it. Without the route, the answer sounds like budget trivia. Without the grand tour, the answer sounds like there was never a larger possibility. Without Mariner Jupiter-Saturn, the answer sounds like Voyager was always a 2-probe brand. Without Triton, the answer misses why Voyager 1 left the farther road. Without Uranus and Neptune, the answer misses the consequence. Without the flyby versus orbiter distinction, the answer exaggerates what a larger mission could have solved. So the long road matters. It lets the simple question become accurate instead of merely catchy. And that's important for the viewer because Voyager is familiar. Familiar stories are easy to flatten. We remember the launch dates. We remember the golden record. We remember the images. We remember the phrase interstellar space. But the title question lives earlier than most of those memories. It lives in the planning years, when the mission was not yet mythic, when every future was still uncertain, when the route was real but the spacecraft were not yet launched. That's the moment this video has been trying to recover. A rare route opened, a larger plan formed around it, a smaller mission survived. 2 spacecraft flew. One path split at Saturn. One spacecraft carried the old road outward, and the worlds it passed still ask for return. Now we can also see why the answer is emotionally balanced. It isn't cynical, because Voyager's success was astonishing. It isn't sentimental, because the mission left major science unfinished. It isn't anti-NASA, because the constraints were real and the compromise produced one of the greatest exploration missions ever flown. It isn't pro-bureaucracy, because the reduction had consequences that lasted for decades. It's the story of exploration under limits. And limits are not the opposite of exploration. They are the material exploration is made from. Every mission has a boundary. The question is whether the boundary destroys the mission or gives it a shape that can survive. For Voyager, the boundary was severe. 2 spacecraft instead of the larger Grand Tour architecture. Jupiter and Saturn as the approved center, Uranus and Neptune as conditional possibilities, a launch window that would not wait, a spacecraft design that had to be ready, a budget that had to be defended. Those boundaries could have made the mission small. Instead, the mission pushed against them until the boundary itself became part of the story. So that's why only 2 no longer sounds like a simple accusation. It sounds like the beginning of an explanation. 2 was what remained after the larger dream met cost and schedule. 2 was what gave the mission redundancy. 2 was what allowed Titan and the ice giant path to coexist. 2 was what let Voyager 2 become the only close visitor to Uranus and Neptune. 2 was not enough to finish the outer solar system, but it was enough to begin the version of outer planet science we still live with. Now imagine holding the 2 spacecraft in your mind again, not as icons on posters, as solutions to a constraint problem. Each one is small against the giant planets. Each one depends on Earth hearing a faint signal. Each one moves through a route no human can stand beside and repair. Each one carries instruments, power, memory, and risk. And together they carry a compromise made under pressure. That compromise became Jupiter's storms, Saturn's rings, Titan's haze, Uranus's tilted magnetic field, Neptune's dark storm, and Triton's active surface. It also became the blank spaces around those discoveries. The years we have not returned, the seasons we have not watched, the moon surfaces we have not mapped, the atmospheres we have not sampled, the interiors we still infer from limited evidence. That combination is the honest payoff. Voyager is not less impressive because it was constrained. Voyager is impressive because it was constrained and still reached so far. The 2-probe answer does not shrink the mission. It gives the mission weight because now we know what those 2 probes were carrying. If we reduce this part of the answer to one sentence, here is the line. Voyager was not the full Grand Tour. It was not a failed 4-probe fleet. It was the 2 spacecraft version of a rare outer planet opportunity that could launch and survive. It split its priorities, and it carried one preserved road all the way to Neptune. Everything else in the story explains why that sentence is true. Deep space missions fail. That simple sentence explains more than it seems to. When a spacecraft leaves Earth for the outer planets, it enters a chain of irreversible events. A launch vehicle has to work. A spacecraft has to separate correctly. Power systems have to stabilize. Antennas have to point. Instruments have to survive. Navigation has to remain precise. Commands have to be received. Data has to return. And all of this happens while the spacecraft is moving toward targets that are years away. Now imagine putting the entire outer planet reconnaissance opportunity on one machine. One launch, one spacecraft bus, one set of power systems, one antenna, one navigation history, one chance to thread Jupiter and Saturn. If that single spacecraft fails, the mission's primary science could disappear with it. A second spacecraft does not remove danger, but it changes the shape of danger. It gives the mission redundancy. It gives planners a second path. It gives science a second chance. So 2 was not just a reduced number. 2 was the minimum architecture that made the mission robust enough to trust. Voyager 2 launched first, but on a slower path. Voyager 1 launched later and traveled faster, reaching Jupiter in March 1979 and Saturn in November 1980. Voyager 2 reached Jupiter in July 1979 and Saturn in August 1981. That sequence gave the team something precious: learning. The first encounter could inform the second. If a camera setting, observing plan, or operational approach needed adjustment, The second spacecraft offered another attempt. Now add trajectory choice. At Jupiter and Saturn, the spacecraft were not just collecting pictures, they were also being aimed. A flyby is both a scientific event and a navigation event. The planet bends the path. A close approach can send the spacecraft somewhere entirely different. That means the mission team had to think years ahead. A decision at Saturn could decide whether a spacecraft ever had a chance at Uranus. Two spacecraft made a fork possible. One could take a path that maximized a high-priority Saturn target. The other could preserve the path farther outward. If there had been only one spacecraft, the mission would have faced a harder all-or-nothing choice. Titan or the ice giants, the nearer prize or the longer gamble. With two, the mission could split its priorities, but why not four, if redundancy and options are good? Because options cost more than the hardware alone. Each additional spacecraft creates another stream of operations. The Deep Space Network has to schedule listening time. Navigation teams have to maintain trajectories. Science teams have to plan observations. Engineers have to monitor health. Software, commands, and contingency plans have to be managed. At Jupiter and Saturn, multiple spacecraft can overlap in ways that strain attention. At Uranus and Neptune, the signals become so weak that every bit of return data has to be fought for. So the number of spacecraft is also a number of promises. Two promises were barely easy. They were not easy at all. But they were more plausible than four in the early 1970s funding climate, especially if the spacecraft could be based on proven Mariner experience rather than a completely new ambitious TOPS design. Now think about launch timing. The late 1970s window did not forgive endless development. A more capable spacecraft that arrives too late is not more capable for this mission. It misses the mission. Heritage matters because it can shorten the path from design to launch. The older Mariner lineage gave the Voyager project something less glamorous than ultimate capability. Schedule credibility. And schedule credibility can be the difference between a mission and a file cabinet. That's one reason Voyager is such a powerful example of constrained exploration. The mission did not use every possible part of the Grand Tour opportunity, but it used enough of it in a form that could be approved, built, launched, and operated. The two spacecraft were not the whole dream. They were the executable dream. Now this does not mean the mission was modest. The word Mariner derived can make it sound like NASA reused an old design and sent it farther. That's not fair. Voyager had to survive extreme radiation near Jupiter, operate in cold and darkness, keep instruments aligned, and return data over distances that stretched the communication system. The spacecraft carried imaging systems, spectrometers, magnetometers, plasma instruments, radio science, and more. They needed attitude control, onboard fault protection, and enough power to remain alive as the sun faded. The two spacecraft architecture also carried emotional risk, because if both spacecraft succeeded at Jupiter and Saturn, the mission would face a choice. It could declare victory at the original targets, or it could keep going into the older Grand Tour possibility. Continuing meant more years of operations, more uncertainty, more dependence on aging hardware, more navigation difficulty, more time waiting for the payoff. We know the answer now. Voyager 2 kept going, but in the 1970s, that future was conditional. It depended on the success of the first encounters and the health of the spacecraft. So when we say NASA only sent 2 Voyager probes, we should hear both halves of the truth. Only 2 compared with the larger Grand Tour concepts, but 2 compared with the much darker possibility of missing the window entirely. The pair gave NASA redundancy, sequence, learning, and a future fork. And that fork became the emotional hinge of the mission at Saturn, because Saturn was where the 2 spacecraft stopped being parallel travelers and became different answers to the same question. Start with a smaller alternative. Suppose NASA had approved only one outer planet spacecraft in 1977. That might sound absurd now, but it's useful as a thought experiment. One spacecraft would have reduced cost and operations. One launch vehicle, one spacecraft bus, one main encounter sequence, one team focused on one path, but one spacecraft would also have made the mission brittle. A launch failure would end everything. A spacecraft failure before Jupiter would end everything. A radiation problem at Jupiter would end everything. A navigation or instrument problem before Saturn could erase the mission's most important science. And at Saturn, one spacecraft would force the Titan versus ice giants decision into a single path. If the spacecraft aimed for Titan, Uranus and Neptune could be lost. If it preserved Uranus and Neptune, Titan science could be sacrificed. That's the power of the two spacecraft architecture. It did not only double the chance of survival, it allowed the mission to hold two futures at once. Voyager 1 could take the Titan path. Voyager 2 could keep going. The pair turned a single fork into a strategy. So when we compare 2 with 4, 2 looks small. When we compare 2 with 1, 2 looks like the minimum serious form of the mission. At launch, each Voyager was a machine with limits. It carried power that would slowly decline. It carried instruments that could fail. It carried a high-gain antenna that had to point back toward Earth. It carried computers primitive by modern standards. It carried a mission plan that depended on planets billions of kilometers apart. And it carried human expectations that changed as each encounter succeeded. Before Jupiter, the mission had to prove it could function in deep space. At Jupiter, it had to survive radiation and return science from the largest planetary system. At Saturn, it had to choose between Titan and the farther road. After Saturn, Voyager 2 had to become something the approved mission had only conditionally preserved: an ice giant explorer. That's not a straight line. That's a chain of survival. Every link mattered. If the launch had failed, there was no mission. If Jupiter had damaged the spacecraft beyond recovery, there was no Saturn success. If Saturn navigation had closed the path, there was no Uranus encounter. If the spacecraft had lost power or pointing or communication, there was no Neptune. If Earth had not upgraded and combined antennas for the faint signal, the farthest data would have been thinner. If budgets had not continued, the old Grand Tour thread could have been cut even after launch. So only 2 hides the depth of what those 2 had to carry. Saturn did not just give Voyager a destination, it forced a choice. To understand why, we need to look at Titan. Before Voyager arrived, Titan was already one of the most compelling objects in the Saturn system. It had a thick atmosphere, unusual for a moon. That alone made it scientifically irresistible. A close look at Titan could reveal chemistry and pressure. It could also show haze and surface clues that no distant telescope could settle, so Voyager 1 was aimed for Titan. That decision carried a cost. The trajectory that brought Voyager 1 close to Titan also bent the spacecraft out of the plane needed to continue toward Uranus and Neptune. In plain language, Voyager 1 took the Saturn system's highest priority moon and gave up the rest of the planetary road. That was not a mistake. It was the mission doing exactly what constrained missions do. It chose a certain scientific prize with one spacecraft, while keeping the farther option alive with the other. Now Voyager 2 becomes more than the second copy. It becomes the carrier of the remaining Grand Tour thread. Its Saturn encounter was planned so the spacecraft could continue outward if the mission was extended and if the spacecraft survived. The difference between the 2 paths is the difference between 2 meanings of success. Voyager 1 secured Titan. Voyager 2 preserved Uranus and Neptune. And here is where we see the 2 spacecraft design fully pay off. If NASA had launched only one Voyager, the Titan choice would have been far more painful. Aim for Titan and the ice giants might be lost. Preserve the ice giant path and Titan receives less direct attention. With 2 spacecraft, the mission did not have to choose only one future. It could split the risk. That split also tells us something about the original "why only 2" question. 2 was not merely half of 4. 2 created a structure. One spacecraft could serve the nearer high-value science, while the other could continue the long gamble. In a smaller mission, that was the maximum amount of strategic flexibility NASA could preserve. Now think about Saturn in November 1980 and August 1981. Voyager 1 reaches first. It passes through a system of rings and moons, returns images and measurements, and flies by Titan. Then it leaves the planetary plane. Its future becomes the long outward journey into the darkness beyond the planets. Voyager 2 arrives later. It studies Saturn too, but its path remains tied to the old Grand Tour possibility. After Saturn, it can be sent toward Uranus, not immediately, not casually. The journey takes years. The spacecraft has to remain alive. Earth has to keep listening. The mission has to keep being funded, but the path remains. Here's the emotional hinge. One spacecraft took the certain prize. One kept the vanishing road open. We can put the answer cleanly. This becomes why the 2 mattered. They were not 4, and that limited the mission. But they were more than 1, and that saved the farther path. Now the story becomes almost improbable. A mission officially narrowed to Jupiter and Saturn, built as the survivable alternative to a larger Grand Tour, ends up sending its second spacecraft onward to the 2 most distant giant planets. Voyager 2 becomes the only spacecraft ever to visit Uranus and Neptune at close range. Not because the approved mission began as a full 4-planet promise, but because the design preserved an option and the spacecraft lived long enough to use it. Here's why Voyager's success can be misleading. The mission worked so well that it can make the earlier reduction feel harmless. We see the photographs of Uranus and Neptune and think the Grand Tour happened anyway. In one sense, Voyager 2 did perform an extraordinary Grand Tour-like extension. In another sense, the limitation remained. There was only one spacecraft on that farther road, one pass at Uranus, one pass at Neptune. No orbiter, no second angle years later, no dedicated ice giant campaign. So the triumph and the cost are inseparable. Voyager 2's continuation proves the 2 spacecraft compromise preserved something priceless. It also shows how narrow the preserved thread was. If Voyager 2 had failed after Saturn, Uranus and Neptune might have waited decades longer for any close look. If its instruments had degraded, if navigation had failed, if budgets had ended, the route would have closed with no second chance. Now we can feel the stakes in a different way. The Grand Tour was not cancelled and gone. Part of it survived inside Voyager 2. But because it survived as one spacecraft, every distant encounter became both a first look and a reminder of how little one flyby can do. That becomes painfully clear at Uranus. After years of travel, Voyager 2 approached a pale blue-green world tipped almost sideways. A planet so poorly known that even a few hours close by would rewrite the textbooks. Science itself created trade-offs. The outer planets were not interchangeable targets. Jupiter mattered. Saturn mattered. Titan mattered enormously because of its atmosphere. Uranus and Neptune mattered because they represented the poorly known ice giants. Triton mattered because it was strange even before Voyager revealed its active-looking surface. Pluto, in the older Grand Tour context, represented another frontier entirely. A mission cannot aim at every target with equal closeness and equal timing. Each flyby geometry favors some observations and sacrifices others. A close pass by Titan changes the outgoing path. A trajectory preserving Uranus and Neptune may give up another viewing geometry. Instrument pointing, data storage, and transmission time all force choices. Here's where the 2 Voyagers became a science priority tool. Voyager 1 could prioritize Titan. Voyager 2 could keep the outer route. The mission did not solve every priority conflict, but it avoided the cruelest version of the choice. Now imagine a single spacecraft. The Triton decision would carry the full weight of the ice giants. Imagine 4 spacecraft. More priorities could be served, but the program might not survive. 2 sat between those extremes, limited but strategically useful. So that's why the fork at Saturn is more than a mission detail. It becomes the place where the 2 spacecraft architecture becomes visible as a decision machine. One spacecraft could cash in the high-value Saturn moon. The other could keep the old Grand Tour possibility alive. Now imagine the most painful counterfactual. Voyager 1 flies past Jupiter and Saturn. It takes the Triton path. It leaves the planetary plane. Voyager 2 reaches Saturn but fails afterward, or loses the ability to continue, or cannot be funded through the extension. Uranus and Neptune receive no close flyby in the 1980s. In that timeline, the 2 spacecraft compromise looks much more limited. The public might remember Voyager as a precise Jupiter-Saturn mission. Triton might still be a major success. The golden record might still become a symbol, but Uranus and Neptune would remain telescopic worlds until some later mission, if one ever launched. That counterfactual shows how much history depended on Voyager 2's survival. The mission's legacy was not guaranteed at launch. The famous all 4 giant planets achievement was contingent. It required the second spacecraft to remain healthy long enough to use the preserved path. It required the ground team to keep the mission alive. It required the spacecraft to keep pointing and communicating. It required the old Grand Tour thread to hold. So Voyager 2 did not merely benefit from the 2 spacecraft decision. It redeemed it. Not by proving 2 was enough, but by proving 2 could be enough to preserve a once-in-generations first reconnaissance. They carried the Jupiter-Saturn baseline. They carried the Triton decision. They carried the Uranus and Neptune possibility. They carried a scientific community's first close look at the giant planets. And eventually they carried the public imagination beyond the planets entirely. But for this video, we should keep the focus where it belongs. Mission architecture and consequence. Voyager 1's later journey into interstellar space matters, but it's not the answer to why NASA sent 2 probes. The answer was written earlier, in the decision to preserve a launchable mission from a larger rare opportunity. By January 1986, Voyager 2 had been traveling for more than 8 years. Earth was far behind. The sun was weaker. Radio signals took hours to cross the distance. The spacecraft was still alive, still controllable, still aimed at a world no human machine had ever visited. Uranus does not announce itself dramatically. It's not banded like Jupiter. It does not wear Saturn's bright rings in the same obvious way. From far away, it can look quiet, almost blank, a pale blue-green disk in the dark. But that quiet appearance is deceptive. Uranus is a planet turned on its side, with a strange seasonal geometry, a system of rings and moons, and a magnetic field that would turn out to defy the simple picture. Now remember the shape of the mission. Voyager 2 was not arriving as an orbiter. It was not breaking into the Uranus system. It was not settling in for years. It was moving through, fast. NASA summaries describe about 5.5 hours of close study during the Uranus flyby, with closest approach on January 24, 1986. At roughly 500 kilometers, 5.5 hours for an entire planetary system. Think about that number. A world that had waited since its discovery in 1781 for close reconnaissance was given a single working day, less than a day, less than most people spend awake between breakfast and bedtime. In that window, Voyager 2 had to image, measure, scan, transmit, and follow a pre-planned sequence while racing past at planetary speed, and it still changed everything. Voyager 2 discovered new moons. It found 2 new rings. It revealed a magnetic field tilted about 55 degrees from the planet's rotation axis and offset from the center. Unlike the simpler picture people might have expected, it showed a system that was not just a distant blue disk, but a complicated ice giant with structures, fields, satellites, and puzzles. Now here is the key discipline. We should not turn that into a list of trivia. The discoveries matter because they show what one flyby can do. A flyby can turn a dot into a system. It can reveal that rings exist. It can find moons. It can measure a magnetic field. It can show that the simple picture was wrong. But a flyby also has hard limits. It sees one moment. It sees certain lighting. It sees certain hemispheres and viewing angles. It passes through the magnetic environment along one path. It cannot watch Uranus through seasons that last decades. It cannot orbit repeatedly and build a global map over time. It cannot drop an atmospheric probe to measure composition directly. It cannot linger over each moon and ask which surfaces are old, which are active, and which might hide internal oceans. So Voyager 2 made Uranus real, but not fully known. That distinction is the heart of the scientific consequence. The 2 spacecraft compromise preserved Uranus reconnaissance. Without Voyager 2, humanity might have had no close look at Uranus at all. But because only 1 spacecraft continued, the reconnaissance was brief. It opened questions faster than it could close them. Now tie this back to the title. Why only 2? Because 2 was the mission that survived. What did that leave? At Uranus, it left a world glimpsed through a narrow window. We can be grateful for the glimpse and still feel the loss. That's not contradiction. That's the honest shape of exploration. Imagine if your only close look at Earth came from a spacecraft racing past once, over 1 set of longitudes, in 1 season. With only hours near the planet, it might discover oceans, it might see clouds, it might detect a magnetic field, it might photograph the moon. It would learn astonishing things, but it would not understand climate, geology, weather cycles, ocean circulation, biology, or the deep interior. Uranus is not Earth, but the analogy helps. A planet is not a single photograph. A planetary system is a changing machine. Rings evolve, magnetospheres respond to the solar wind, atmospheres circulate. Moons preserve histories in their surfaces. Some moons may hide oceans. A flyby can reveal the machine exists. An orbiter begins to watch it work. Voyager 2 could not do that. It was never designed to become a Uranus orbiter. It did not carry the fuel, mission architecture, or trajectory plan for that. It was using Uranus as another encounter on a flyby path. Its job was reconnaissance, not residence, and yet the reconnaissance was enough to make Uranus scientifically urgent. The tilted magnetic field alone told scientists that ice giants might not behave like scaled versions of Jupiter and Saturn. The moons and rings gave the system texture. The planet's bland, visible face raised questions about atmosphere, heat, seasons, and interior structure. The flyby did what first reconnaissance often does. It replaced ignorance with sharper ignorance. Sharper ignorance is progress. Before Voyager, we did not know what questions to ask. After Voyager, we did, but asking better questions is not the same as answering them. So that's why Uranus remains one of the cleanest examples of Voyager's dual legacy. The mission was reduced, yet it reached the planet. The flyby was brief, yet transformative. The data were historic, yet incomplete. The second spacecraft carried the old Grand Tour possibility farther than anyone could demand. But one pass still left generations of science waiting. Now Voyager 2 moved on. Beyond Uranus lay Neptune, even farther from the Sun, even harder to reach, and carrying one of the strongest consequences of all, Triton. A strange moon that would make a single flyby feel almost unfairly brief. Finally, there's the flyby constraint. Even if NASA had flown more Grand Tour spacecraft, the basic mode of exploration would still have been fast reconnaissance. Flybys are magnificent, but they are brief. They are how a civilization gets its first close look. They are not how a civilization fully studies a complex planetary system over time. This matters because it keeps the opportunity cost honest. At Uranus, Voyager's hours of close study were historic, but they could not replace an orbiter. At Neptune, the close pass was astonishing, but it could not settle the long-term behavior of the system. At Triton, seeing activity was enough to make the Moon compelling, not enough to understand it completely. More flybys would have improved the first reconnaissance. They might have provided backups, alternate geometries, and more target coverage. But they would not have done the work of a Uranus orbiter and probe. They would not have watched seasons. They would not have repeatedly mapped magnetospheres. They would not have put a probe into an atmosphere unless designed to do so. So that's why the modern science gap is not only the result of sending 2 instead of 4, also the result of not yet returning with a different mission class. Voyager opened the door. It did not build a house there. Now suppose the fuller grand tour had worked. More spacecraft reach the outer planets. Uranus and Neptune get more than one pass. The dataset is richer. Different geometries reveal different moons, rings, fields, and atmospheric features. Some measurements are repeated. Some failures are covered by backup spacecraft. The scientific record becomes broader. That would have mattered. We should not minimize it just because Voyager succeeded. A larger flyby campaign could have changed planetary science. It could have given researchers more confidence in patterns and anomalies. It could have reduced the dependence on one spacecraft's viewing geometry. It could have made the ice giants less lonely in the data archive. But even in that better timeline, the next question would remain. When do we orbit? A flyby fleet can improve reconnaissance. It cannot turn Uranus into a studied seasonal system. It cannot watch Neptune's weather for years. It cannot revisit Triton repeatedly unless the trajectory allows it. And even then it remains a pass, not a home. It cannot replace atmospheric probes or long-duration magnetosphere mapping, so the larger grand tour would have changed the baseline. It would not have ended the need for dedicated return missions. Here's important because it keeps the emotional scale honest. The lost opportunity is real. It's not infinite. Regret asks, what did we miss? Consequence asks, what did the mission make visible? And what does science still need because of it? At Uranus, the consequence is not just that more pictures would have been nice. The consequence is that Voyager found a planetary system whose magnetic field, moons, rings, atmosphere, and interior demanded more than a flyby could provide. The weirdness was not decorative. It changed the category of the problem. Uranus became an example of how little we understand ice giants. Neptune was the farthest giant. By the time Voyager 2 approached it in August 1989, the spacecraft had traveled for 12 years. The mission that began as a narrowed Jupiter-Saturn compromise had reached a world so distant that sunlight there's faint, radio signals are fragile, and every command feels like a conversation with the past. JPL has described the Neptune flyby as both a first and a last. It was humanity's first close-up of Neptune. It has also remained the last because no spacecraft has returned since. That's not hype. It becomes the plain weight of the calendar. Now think about the engineering. Voyager 2's transmitter was tiny by Earth standards, with public JPL accounts describing about 13 watts of power. From Neptune, that whisper had to cross billions of kilometers. The deep space network had to be strengthened for the encounter, including upgrades and antenna combinations so Earth could catch as much data as possible. The spacecraft was operating in low light, at extreme distance, with a long command delay. After more than a decade in space, and still it delivered Neptune. Voyager 2 found a dynamic atmosphere, including the Great Dark Spot, a huge storm system seen during the flyby. It revealed rings and new moons. It showed that Neptune, far from the Sun, was not a dead blue ball. It was active, structured, weather-bearing, a real world with motion and surprise. But Neptune was only part of the encounter. The deeper emotional science came from Triton. Triton is Neptune's largest moon, and it's strange from the start. It orbits in a retrograde direction, meaning it travels around Neptune opposite the planet's rotation. That's a strong clue that Triton may be a captured object, something Neptune seized long ago rather than a moon that formed quietly in place. Before Voyager, Triton was distant and mysterious. After Voyager, it became one of the most intriguing moons in the solar system. Voyager 2 saw geologically young terrain. It saw evidence of activity, including geyser-like plumes rising from an extremely cold surface. It photographed much of Triton's visible face during the encounter. It revealed a world that looked less like a frozen relic and more like a captured body still capable of change. And then Voyager left. That's the line that makes Triton different. The spacecraft found a moon that practically begged for return, then had no ability to stay. It could not orbit Neptune. Once it passed Triton, every unanswered question became work for a future mission. No seasons watched, no changing plumes followed, no interior story tested over time. Voyager gave Triton one astonishing look, then carried the question away. Now the title question has become a scientific feeling. Only 2 Voyager probes meant only 1 spacecraft reached Neptune. Only 1 spacecraft meant 1 encounter. 1 encounter meant Triton became a question more than an answer. But we need to keep our balance. It would be wrong to say a larger Grand Tour flyby program would have solved Triton. More flybys might have provided different angles, backup observations, or other targets. They would have mattered. But unless a spacecraft entered orbit or returned for extended study, Triton would still not be fully understood. The issue is not that NASA missed an obvious complete solution. The issue is that the reduced mission preserved reconnaissance, not residence. Neptune makes that distinction vivid. Voyager 2 passed about 4,800 kilometers above Neptune's cloud tops at closest approach, according to NASA summaries. That's incredibly close in planetary terms. Also, incredibly brief. A fast flyby turns distance into revelation for a moment, then returns the world to distance. The spacecraft cannot stop unless the entire mission is designed around stopping, and stopping at Neptune requires enormous energy and a very different architecture, so Neptune became the farthest proof of Voyager's brilliance and incompleteness. Brilliance, because a 2 spacecraft mission approved for Jupiter and Saturn managed to send 1 machine to Neptune 12 years later. Incompleteness, because the first close look remains the only close look. Now look back at the original Grand Tour dream. It promised a broader reconnaissance of the outer solar system during a rare window. Voyager 2, almost impossibly, carried that spirit to all 4 giant planets. It did more than the narrowed mission had any right to demand. But it did it as one surviving thread, not as the full woven fabric of a larger campaign. So that's why the story should not become cynical. If we focus only on what NASA did not fly, we miss the miracle of what did fly. If we focus only on the miracle, we miss the scientific cost. GNS lives in that middle space. Gratitude without amnesia, consequence without grievance. Neptune and Triton also show why the public memory of Voyager can become too tidy. We remember the photographs, the blue planet, the strange moon, the feeling that humanity reached the edge of the known planets. But science does not end at first sight. Often, first sight is where science begins. A single flyby can reveal a storm, but not a climate. It can reveal a plume, but not a cycle. It can reveal a magnetic field, but not its long-term behavior. It can reveal a moon's face, but not its full history. Voyager 2 gave us the first answers at Neptune. It also gave us better reasons to go back. Before we turn that into regret, though, we need one more correction. More spacecraft would have helped. More flybys would have mattered. But even the larger Grand Tour would still have been a reconnaissance program. To understand what was fully left unfinished, we have to separate flyby science from the deeper work of orbiters and probes. Communication may sound like a background detail, but at the outer planets it becomes part of the mission's spine. A spacecraft can make the greatest measurement in history, but if Earth cannot receive the data, the science is lost. At Uranus and Neptune, signals are weak, travel times are long, and the spacecraft's power is limited. JPL's public accounts of the Neptune encounter emphasize how much the ground system mattered, including antenna upgrades and combinations to catch Voyager's faint transmission. Now multiply that by more spacecraft. More spacecraft can mean more data, but also more scheduling, more tracking time, more command planning, and more potential conflicts around critical encounters. The Deep Space Network is not a magical infinite ear. It becomes a real system with antennas, locations, maintenance, and competing missions. The farther a spacecraft goes, the more precious each listening opportunity becomes. Voyager's 2 spacecraft mission already demanded long-term ground commitment. A larger Grand Tour fleet would have demanded more. That does not mean it was impossible. It means communication was part of the cost and risk picture, not an afterthought. And communication also affects science strategy. At Neptune, Voyager could not transmit unlimited high-resolution data. The team had to plan what to collect, what to store, what to send, and how to use the available link. A flyby at extreme distance is a choreography between the spacecraft and Earth's ability to listen. That's another reason the 2-probe answer is deeper than budget alone. The mission was constrained by the entire Earth-to-space system. At Neptune, the consequence is not just that no one has returned. It's that the one spacecraft that did go found a dynamic atmosphere and a moon, Triton, that may be a captured world with active geology. A captured active moon around the farthest giant is not a footnote. It becomes a major scientific target. At Triton, the consequence is especially sharp. A flyby can reveal plumes, young terrain, and strangeness, but it cannot watch a captured world over time. It cannot fully map the surface. It cannot test every model of interior activity. It cannot tell us how the system evolved from one brief encounter. So that's why modern mission priorities matter so much in this story. The Decadal Survey's Uranus Orbiter and Probe recommendation is not a romantic longing for Voyager's era. It becomes the science system saying, this gap remains central. We need an orbiter, we need a probe, we need time in the system. We need to understand ice giants because our own solar system has 2, and the galaxy seems to have many worlds in that size range. Here is the necessary correction. More spacecraft would have mattered, but more flybys are not the same as complete knowledge. This matters because the story can easily slide into exaggeration. We can imagine the lost Grand Tour as if it would have solved Uranus, Neptune, and Triton forever. 4 spacecraft instead of 2. More encounters, more data. So, no mystery left. That's not how planetary science works. A flyby is reconnaissance. It becomes a fast pass through a system. It can take images, measure fields and particles, observe rings and moons, and transform a distant dot into a place. It's one of the most powerful tools for first discovery. But it's not the same as living with a planet. An orbiter is different. An orbiter returns again and again. It sees changing light. It maps different regions. It watches weather evolve. It samples the magnetic environment from many positions. It can revisit moons, compare surfaces, and build context over months or years. If a flyby is a first conversation, an orbiter is a relationship. An atmospheric probe is different again. A probe enters a planet's atmosphere and measures directly. It can sample composition, temperature, pressure, winds, clouds, and chemistry in ways remote sensing cannot fully replace. For giant planets and ice giants, that direct vertical profile can be essential. Now let's use that distinction on Uranus and Neptune. A larger Grand Tour style flyby architecture might have given us more looks. It might have improved redundancy. It might have observed different targets or angles. It might have reduced the chance that one instrument problem or one geometry limitation shaped our entire close-up record of an ice giant. That would have been valuable science, but it would still not have watched a Uranian season. It would not have orbited Neptune for years. It would not have mapped Triton's active regions repeatedly. It would not have dropped probes into both ice giants unless the mission was designed for that very different purpose. It would still be a first reconnaissance, just a broader one. Here's why the opportunity cost is real but bounded. Real, because the rare route could have returned more first-look data than the two spacecraft mission did. Bounded, because the worlds themselves require more than flybys to understand. That balanced view protects Voyager from both extremes. It keeps us from saying NASA made no sacrifice. A larger use of the window could have changed the first record in lasting ways. It also keeps us from pretending that the full Grand Tour would have finished outer planet science. It would not. It would have opened the next era with more information. Now listen to how that changes the emotional answer. The tragedy, if we want to use that word quietly, is not that NASA missed a perfect solution. The tragedy is that the first step was narrower than the opportunity allowed, and the second step has taken decades to arrive. Voyager revealed enough to make return missions scientifically urgent, but the outer planets are so far away and missions are so expensive that urgency does not automatically become hardware. Uranus is still waiting. Neptune is still waiting. Triton is still waiting. And their waiting is not empty. It's filled with questions that Voyager sharpened. What is inside an ice giant? How do Uranus's unusual magnetic field and extreme axial tilt interact? Why does Neptune emit and move energy the way it does so far from the Sun? What happened to Triton when Neptune captured it? Could some outer moons hide oceans? How do ice giants in our solar system help us understand the many similar-sized worlds found around other stars? Voyager did not fail to answer these questions. Voyager made the questions possible. That's the right tone. Not accusation, not sentimentality. Clarity. The two spacecraft compromise preserved a first look at all four giant planets through Voyager 2. It gave us Jupiter and Saturn. Then, through Voyager 2, it gave us Uranus and Neptune in one mission arc. It gave us enough to know that the ice giants were not afterthoughts. But because it was a flyby architecture, and because the larger Grand Tour did not fly, the outer solar system remained thinly sampled. Now we can see why modern planetary science keeps returning to Uranus and Neptune. The interest is not nostalgia for Voyager. It becomes the scientific consequence of Voyager's limits. So the next step in the evidence is not about relitigating what NASA should have done in 1972. It becomes about what the unfinished science looks like now, after Voyager's data have been sitting at the foundation of ice giant research for decades. There's another tempting alternative. Wait. Wait for better electronics, better instruments, better launch vehicles, better budgets, better computers, better cameras, better everything. In ordinary life, waiting for better tools can be wise. In a mission window story, waiting can be dangerous. The future spacecraft may be better, but the old gravity assist chain may be gone. The destinations remain, but the route changes. A better machine launched too late may face a worse path. So now we can see why Voyager's timing matters so much. The spacecraft were not modern by our standards. Their computers were tiny. Their cameras were limited compared with later systems. Their data rates were slow, but they were ready when the planets offered the route. A future mission could be more capable and still not reproduce the same Grand Tour geometry. Here's the deep reason exploration cannot be planned as pure technological progress. Sometimes the sky presents a deadline before technology has reached perfection. The choice becomes whether to fly a good enough mission now or risk a better mission later that no longer has the same path. Voyager chose good enough. Then it became extraordinary. Each road not taken clarifies the road that was. One spacecraft would have been cheaper but brittle. 4 spacecraft could have been richer but more vulnerable. Waiting could have improved hardware but lost geometry. More flybys could have expanded reconnaissance but still left orbiter science undone. A failed Voyager 2 would have revealed how thin the preserved Grand Tour thread was. The actual mission sits in the middle of those alternatives. Not the least ambitious, not the most ambitious, not the complete answer, not a failure, a constrained architecture that caught a rare route and then outperformed its official shape. So that's why the final answer should feel calm rather than angry. The history is not asking us to choose between worship and blame. It asks us to understand how exploration works when physics, engineering and science all press on the same decision. Money and time press on it too. And once we understand that, the two Voyagers carry more weight. They were small in number, but huge in burden. They carried a reduced mission and a surviving Grand Tour option. They carried the first close study of the giant planets, and they carried the unfinished questions that still point us back toward Uranus, Neptune and Triton. That's the version of Voyager worth remembering. The clearest evidence that Voyager left unfinished science is not a complaint from the past. It becomes a priority in the present. Decades after Voyager 2 flew by Uranus and Neptune, the planetary science community still treats the ice giants as major unfinished worlds. The 2022 Planetary Science and Astrobiology Decadal Survey recommended that NASA begin work on a Uranus orbiter and probe as a large strategic mission. That recommendation is not nostalgia. It becomes a statement that one of the most important planetary systems in our own solar system remains poorly understood. Now think about what that means. Jupiter has had orbiters. Saturn had Cassini for years. Mars has been watched by orbiters, landers and rovers. The Moon has been mapped in extraordinary detail. Even small bodies have received dedicated missions. Uranus and Neptune, by contrast, still rest heavily on Voyager 2's brief encounters. That imbalance matters because ice giants may be common beyond our solar system. The Decadal Survey notes that more than 30% of known exoplanets are ice giants or ice giant-size worlds. In other words, the kind of planet we understand least in our own system may represent a very common planetary outcome elsewhere. And this becomes where Voyager's limit becomes larger than Voyager itself. When astronomers find a planet around another star that sits near the size range of Uranus or Neptune, they are not comparing it with a fully understood local template. They are comparing it with worlds we have barely visited. The exoplanet revolution made the ice giants more important, not less. It turned Uranus and Neptune from distant leftovers into reference cases for a galaxy full of similar-sized worlds. The old flyby data now has to support a much wider question. That should bother us in a productive way. We are trying to understand planets around other stars while our local examples remain underexplored. Uranus and Neptune are not remote trivia. They are laboratories. They hold clues about planet formation, interior structure, atmospheric dynamics, magnetic fields, rings, moons, and migration histories. They help us ask what kinds of planets the galaxy makes. Voyager gave the first close measurements. It did not give the final framework. At Uranus, scientists still want to understand the planet's internal structure and composition. They want to know why its magnetic field is so strange. They want to study its atmosphere over time, not just in one flyby moment. They want to understand its rings and 27 known satellites, some of which may have hidden oceans or geological histories that Voyager could not resolve. At Neptune, the questions are just as sharp. What drives its weather so far from the Sun? How does its interior work? What is the full history of Triton, a likely captured moon with active geology? What does the Neptune system tell us about migration, capture, and the outer solar system's violent past? Now bring this back to Voyager. The 2 spacecraft mission did not create these unanswered questions by failing. It exposed them by succeeding. Before Voyager 2, Uranus and Neptune were mostly distant ideas. After Voyager 2, they became systems with specific mysteries. The Flybys changed ignorance into a research program, but the research program still needs spacecraft. That's where the bill comes due. A temporary road opened in the late 1970s. NASA used part of it with 2 spacecraft. Those spacecraft did more than expected, yet because the broader architecture did not fly, and because no dedicated ice giant orbiter has followed, the data gap remains enormous. Here's the scientific afterlife of only 2. It's not a scandal. It's not proof that Voyager was a failure. It becomes the long shadow of a constrained success. Now, when we talk about a future Uranus orbiter or a Neptune/in mission, we are talking about the next step after Voyager, not a replacement, not a correction of a mistake, a continuation of a question Voyager made unavoidable. What would it take to go back? The answer is hard. It would take years of development, a launch window, a powerful trajectory, long cruise time, radioisotope power, deep space network support, instruments designed for ice giant science, enough political and budget support to last through a mission whose payoff may come far beyond one election cycle. In other words, it would require many of the same categories of constraint that shaped Voyager, so that's why this story still matters. Voyager is not just a past tense achievement. It becomes a lesson in the physics and politics of reachability. Some destinations are not merely far, they are time-sensitive, institution-sensitive, technology-sensitive. A path can be open in the sky and still difficult on Earth. Now the session continuation becomes natural. If we want to understand why Uranus remains almost unexplored, Voyager is the starting point. If we want to understand why returning to Neptune and Triton is so difficult, Voyager is the starting point. If we want to understand where the solar system ends, Voyager is again the starting point. Because after the planets, the spacecraft kept going into the heliosphere and beyond. But this video's question is narrower. Why only 2? By now the answer has several layers. The route was rare. The larger Grand Tour and TOPS concepts were real. The full architecture was too costly, too technically ambitious, too schedule sensitive, and too vulnerable for the early 1970s environment. The approved mission narrowed to 2 Mariner-derived spacecraft aimed first at Jupiter and Saturn. Those 2 gave redundancy and strategic flexibility. Voyager 1 took the Titan path. Voyager 2 kept the old road open, and the worlds left behind show why that mattered. Now we can close the circle. Once Voyager launched, time did not stop being a constraint. The spacecraft spent years between encounters. During those years, teams had to maintain knowledge, funding, hardware support, software expertise, and scientific attention. A mission to Neptune is not just hard because Neptune is far away. It's hard because the people who design the early sequences must plan for events more than a decade later. That long duration changes institutional risk. A short mission can fit more easily inside a budget narrative. A multi-decade mission becomes a promise passed from one year to the next. The farther the payoff, the more chances the environment on Earth has to change. Voyager survived that passage. But again, survival should not be mistaken for inevitability. The fact that Voyager 2 reached Neptune does not mean any architecture would have survived to Neptune. It means this particular architecture, with this particular spacecraft and team, did. Now think about a larger Grand Tour fleet under the same time pressure. More spacecraft would have created more long-duration obligations, more encounter sequences, more aging hardware, more extended operations, more data management, more chances for support to waver before the final worlds were reached. That does not make the larger concept wrong. It makes it fragile. A final scale check helps here. The Voyagers were not sent into an empty dark for symbolism. They were sent into a working solar system where every planet's motion mattered. Jupiter was not just a destination. It was a machine for changing the spacecraft's future. Saturn was not just a ringed planet. It was the place where Titan and the Father Road forced a choice. Uranus and Neptune were not bonus worlds. They were the proof that the preserved path still had power. Triton was not a footnote. It was the object that made one flyby feel almost painfully brief. So when we picture the mission, we should not picture two probes against generic stars. We should picture two probes inside a chain of consequences. The first consequence was practical. The mission had to launch in time. The second was architectural. The larger Grand Tour became a smaller two-spacecraft mission. The third was strategic. The two spacecraft could split their futures. The fourth was scientific. Voyager 2 revealed ice giant systems that demanded return, and the fifth is still with us. Modern planetary science continues to ask questions that one fast reconnaissance could not answer. That's the full scale of only two. It begins as a number. It ends as a map of everything those two spacecraft preserved, and everything they could not possibly finish. If a future Uranus mission flies, it will not merely be correcting Voyager, it will be building on Voyager. The old flyby data will help define the questions. The strange magnetic field, the rings, the moons, the atmosphere, the unresolved interior, all of these became sharper because Voyager 2 passed by. The same is true for Neptune and Triton. A future mission would not begin from zero. It would begin from the first reconnaissance. That's how exploration often works. First you see enough to know where ignorance lives. Then, if the institution can survive the cost and time, you return with better tools. The hard part is that the return is not automatic. The same kinds of constraints come back. Launch windows, trajectories, power, communications, long cruise times, budget cycles, competing priorities, technology readiness, scientific advocacy. The planets are still far away, and the human system is still finite, so Voyager is not only a story about a closed window, also a warning about every future window. When a rare route opens, the sky may be ready before the institution is. When a scientific target becomes urgent, the technology may still need years. When a mission is affordable enough to launch, it may be too narrow to answer everything. When a mission is broad enough to answer more, it may become too fragile to survive. That's the real lesson, not cynicism, not defeat. Design under constraint. The Voyagers are often described as ambassadors, and that's true in a cultural sense. They carry golden records. They continue outward. They have become symbols of humanity's reach. But in the context of this question, they are something else too. They are evidence that exploration is shaped by compromise before it becomes poetry. The poetry came later. First came trajectory plots. First came cost estimates. First came spacecraft trade studies. First came arguments over priorities. First came the hard decision to fly a smaller mission while preserving one path outward. And then, because the spacecraft worked, the compromise became historic. Imagine the alternative ending. Suppose NASA had refused the smaller mission because it was not the full Grand Tour. Suppose the larger architecture failed too late to replace. Suppose the route closed with no Voyager launch in 1977. We would not be debating why only two. We might be asking why none. That possibility does not prove the two spacecraft decision was perfect. It proves the decision was made in a field of imperfect choices. Perfect choices are rare in deep space. A mission can be too small. A mission can be too large. A mission can be scientifically ideal and institutionally impossible. A mission can be compromised and still change civilization's understanding of the solar system. Voyager belongs to that last category. It was compromised. It was magnificent. Both statements are true. We can answer the title without anger and without smoothing away the loss. NASA sent only 2 Voyager probes because the fuller Grand Tour vision could not survive the combined pressure of cost, schedule, technical ambition, budget politics, launch timing, and risk. The two spacecraft Mariner Jupiter-Saturn mission was the version that could fly. Within that version, planners preserved one long road outward. Voyager 2 used it. What did that leave unresolved? Enough to shape the next half-century of outer planet science. So that's why the ice giants still matter here. They are not side quests. They are the evidence of the decision's boundary. Uranus and Neptune show what first reconnaissance can accomplish. They also show what first reconnaissance cannot do. Triton shows how a single encounter can reveal a world so strange that the absence of a return mission becomes part of the scientific story. And that's why the two Voyagers should feel more impressive, not less, after we understand the constraint. They were not the full Grand Tour. They were the part of the Grand Tour that escaped Earth. They were the version of the road that survived. That achievement can confuse us, because success softens the appearance of constraint. If Voyager 2 had failed after Saturn, the story would feel different. We would talk more openly about the lost ice giant reconnaissance. We would see the two spacecraft compromise as smaller and riskier. We would remember the Grand Tour as a vanished chance. But because Voyager 2 survived, because the navigation worked, because the spacecraft kept talking, because the ground teams kept listening, the reduced mission became a legend, and legends can hide how close they came to not happening. Now think about the missions that did not exist. They were not approved hidden Voyagers. They were alternative futures. A more ambitious top spacecraft, a fuller launch set, different trajectories, more outer planet encounters, more redundancy beyond Saturn, more ways to sample the ice giants and perhaps Pluto. Those futures lived in studies, proposals, and planning arguments. They did not become hardware in the way Voyager 1 and Voyager 2 did. That difference between a studied future and a flown spacecraft is one of the hardest things in space history. A paper mission can be perfectly logical. It can be scientifically beautiful. It can have the support of serious people. It can deserve to happen. And still, if it does not survive funding, engineering, schedule, and launch, it never crosses from possibility into evidence. Voyager crossed. So that's why the two spacecraft deserve so much respect. Not because 2 was enough for the outer solar system. It was not. Not because the larger Grand Tour was foolish. It was not. But because 2 was the fragile bridge between a rare planetary pattern and actual data from worlds humanity had never seen close up. Make the bridge physical. So why did NASA only send 2 Voyager probes? Because the rare gravity assist route was only the first requirement. The planets created a temporary road through the outer solar system. That road made a broader Grand Tour conceivable. NASA, JPL, and the planetary science community studied larger concepts, including Grand Tour and TOPS architectures with more launches and more ambitious spacecraft. Those concepts were real, they mattered. They are why the question still feels powerful. But they were not the same thing as an approved Voyager 3 and Voyager 4 fleet. The mission that survived approval was smaller. It was the 2 spacecraft Mariner Jupiter-Saturn mission, renamed Voyager shortly before launch. It focused first on Jupiter and Saturn because that was the version that could fit the cost, schedule, design heritage, launch timing, and risk NASA could carry in the early 1970s. 2 was a reduction, but 2 was also a survival strategy. With 2 spacecraft, NASA had redundancy, it had sequence, it had a way to split priorities. Voyager 1 could take the scientifically precious Titan path at Saturn. Voyager 2 could preserve the longer gamble toward Uranus and Neptune. Without that second spacecraft, the ice giants might have remained unseen at close range for far longer. Without the compromise, the mission might have missed the road entirely. That's the answer's shape. Constrained success with real opportunity cost. Voyager 2's brief flybys of Uranus, Neptune, and Triton were extraordinary. They changed distant names into places. They revealed rings, moons, strange magnetic fields, storms, and active geology. But they were flybys. One pass, one moment. They did not replace orbiters, they did not settle the ice giants, they did not finish Triton. By the end of this video, the promise was not to show that NASA lacked ambition, or that approved extra Voyager probes were cancelled. The promise was to show why the actual answer is more interesting. Voyager was the surviving fragment of a larger rare opportunity, and those two spacecraft carried that opportunity farther than a reduced mission had any right to go. The destinations remained after the road closed. That's the quiet power of the Voyager story. The planets are still there. Uranus is still waiting for an orbiter. Neptune and Triton are still waiting for return. The questions are still alive because Voyager did not end outer planet science. It began the deeper version of it. And that leads naturally to the next question. Not why Voyager stopped, but what it would take for us to go back to the ice giants and finally stay. So the closing is not that the mystery has disappeared. The closing is that the evidence has become more disciplined. We can say what the measurements support. We can also say where they stop. That distinction is the difference between a satisfying answer and an exaggerated one. It leaves us with a quieter kind of wonder. Not the wonder of a solved riddle, the wonder of a physical system that keeps more of its history than it first seemed to keep. And that's enough to change the way we look at the original question. It's no longer just a question about an object in space. The next natural question is how far those two surviving machines can keep traveling once the mission itself has faded behind them.